Hi everybody, I want to welcome you to a bit of an interesting, a little special edition of Cutting Code. So what I want to do in this session is actually revisit the session that we streamed on Sunday. So on Sunday we worked on the Conways Game of Life kata. It's a nice little fun zero-player game. So in front of me on my screen there's the description of Conway's Game of Life. So it's a cellular automation game devised by the mathematician John Horton Conway in 1970. So it's basically a simple math simulator of life. It's got a couple of simple rules. You generate an initial state, and then there's a couple of rules. So the initial state is made up of a series of cells, and if I just scroll down a little bit in this description, living cells as the game ticks and changes state. If a cell has more than 2 living neighbours, the cell dies. If it has greater than 3 living neighbours, the cell dies, so underpopulation and overpopulation. But if it has between 2 and 3 living neighbours, the cell lives. So as a dead or empty cell, when the game ticks, it also changes state. And if a cell has 3 living neighbours, it lives. So we've got this little ecosystem simulator that runs. So on Sunday, I built this test-driven implementation of Conway's Game of Life, and it was a little bit of a tricky session despite the fact that it shouldn't have been, and I kept on running into these really interesting, annoying bugs. And after I slept on it for a little while, I realised that the reason that it was difficult is that my tests were really poor. So when I scan down some of these tests, I mean, they don't look like poor tests on the surface, you know. Got reasonable names, given dimensions, things are not null. We're checking if the board's not null. You know, this test is okay. We're checking that cells are populated in the board. You know, all these kind of things. They kind of look okay on paper, but when you get down to here, you know, step, given 1 living cell dies, all of a sudden you start to reach this horrible mismatch between the problem we're actually trying to solve and the way that the tests express themselves. And I was walking around on Monday morning, and I realised that the reason that I was building a buggy implementation that I was struggling to debug and find the tests in is that the tests actually don't visually represent the thing that I'm trying to build. The tests don't look like the output of the code. And actually that's a bit of a problem, because your test should be so readable that as you work through a problem, it's obvious what the correct behaviour should be. So I'm going to pull up my browser over here. I'm going to show you what Conway's Game of Life looks like running. So if I just Google it, there's a cool little Easter egg on Google that runs a Game of Life simulator. So it's cute. That's basically what it looks like running. You get all these kind of repeated shapes. And really, if I am building a test to simulate Conway's Game of Life, I really should be building tests that look like it looks. That's important. So I spent Monday evening reading over some of these tests, and they're just horrible. The amount of mental parsing that you have to do to turn this into something that looks like Conway's Game of Life is unreal. So I'm not very happy with this implementation. I think it sucks. So there are some good things about it. I think the cell generator was kind of cool. I would keep that. I think that the renderer kind of works, but in a better implementation might not be required. And I think the Game of Life board in its current form is actually kind of okay, though this is a little bit nasty, and I think this is pretty horrible too. But what I want to do is actually focus on how I would write the tests better to better express the Game of Life. So if I jump back into the game board renderer tests, I want to take a look at what I'm doing. So first and foremost, I just want to prove to you that this runs. There it runs. See, we can see a Game of Life, and it does play out. So what the simulator does is it generates an initial state and then just executes. So that's all well and good, but I want to kind of start again. But the important thing this time is that the tests need to look like the desired output. So I'm going to do another game board 2. I'm just going to do game board 2 tests. Let's think about this from a really outside-in perspective. So one of the initial problems is the way that the stories were broken down implied that the game board needed to generate an internal initial state, but actually for the purpose of this exercise I want to supply the board with a state, and we want to drive that out. So, constructor given state splits representation into some kind of internal model. Okay, so I kind of like the fact that I can assert on widths and heights. So I want to say a new game board equals new game board 2, and again pure TDD, so we don't have an implementation yet. But actually, instead of letting game board 2 generate its own internal state, I want to give it one. So obviously, if we wanted to generate a state, we could build this model up outside of the game board. So what I want to do is I want to make sure my tests actually look exactly like the Game of Life. So a Game of Life game board, maybe we could trivially render it as maybe a dash for dead, or a cross for dead and a 0 for alive. So given a game board that looks like this, in fact let's use letters. Alive, dead, dead, dead. A 4x4 game board. I'm also going to trim it just for the string manipulation. So if I have a game board that looks like that and I pass it in, I now want to assert that game board width is equal to 2, and I want to assert that game board height is equal to 2. So what I really want to see is if by building my tests out this way I'm driven to a completely distinct and different implementation I was by focusing on kind of an internal object model in the first attempt. So actually, let's do the simplest things that could possibly work all the way through. So we got a string. We have a string, nothing more. And, you know, maybe a string is split into a series of lines. So, width and height, let's create those properties. So we're going to use resharper just to generate this stuff. Right, so let's drag these up here. So we've got an internal state and a width and height. So in order to make this test pass, very, very simply, I mean I can cheat. Great, so my test passes. So let's write another test to make it fail. CTOR given 5x5 board, width and height set. And actually that's more like the legitimate name of this. Given 2x2 board, width and height set, given 5x5 board. I'm going to basically write the same test here, but I'm expecting 5x5, so alive, dead, 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 dead. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So that's a 5x5 game board. Obviously this test now fails because it was just hard coded. So what I'm actually going to do is I'm going to convert the internal state into a list of strings. That seems plausible. And I'm going to say var state equals state dot split on environment new line. Oh, and of course there's the idiosyncrasy of the string split. New array, new line, string split options, none. And then I think I probably have to convert this to a list. Great, so I now have a list of lines. So the cool thing about this is I suspect I can probably, exactly, because strings can be indexed by the character offset and lists can be accessed by their line offset, I can reference individual cells pretty trivially. That's nice, it means I don't have to marshal this into an object model of any kind. But this is obviously failing, so why is this failing? Because my width and height are still hard-coded. So width, I'm going to turn into a calculator property, is state max length. We'll go with it. Return. And height is state count. So now those tests should pass, he hopes. Great. Green, green, green. So as you can see now, my unit tests more accurately reflect the state of Conway's game of life. So instead of having to concern myself with splitting out rendering and all that kind of stuff, I'm just going to dive straight into implementing the rules of the game of life and see if I can do it with minimal fuss. So let me just flick back to the rules in here. So there's a couple of things to bear in mind: whether the cell is living or dead, and the numbers of neighbours that appear in the cells. So let's start with the first scenario, which is, we'll start with the dead case. I think it's the easiest thing to test. So I'm going to take a look at this. So it seems like it's all about 3 neighbours, 3 or more. So let's, if we go with a 4x4 base test case, so I'm just going to grab this, I'm going to write another test, and I'm going to say step, I'm going to say cells are all dead, nothing lives. Nice and simple, the simplest test I can imagine here. And we want to work with a 4x4 from here on in, I think. So 1, 2, 3, 4, kill that line, there we go, there, 4x4. And actually, if I do this, at least I can create my game board in its initial state. So I wonder, if I do this, will something crazy happen? No, it won't, because it trims all the white space. That's excellent. What I'd really like. So I think actually all of these lines now are too long. So what I'm going to do is I'm just going to assert that that's correct. And I think it should be 4x4, but I don't think it's going to be. I think it's going to be something stupid. Yeah, it's going to be 49 or something. Okay, great. So I can't do that because this white space here actually counts. That's not a problem. So I'm going to drop this line and bring all this back. Okay, it's perfectly readable. I don't like the fact that the code is aligned to the left here, but it's kind of good enough. Okay, so cells are all dead, nothing lives. So game board step. Right. I'll just auto-complete it so it throws an exception. And I want to assert that game board to string is equal to my expectation. So what I'm doing here is I'm pulling away from the previous implementation's need to write tests that look like this. No, that's the wrong file. Game of Life board tests. These are the tests I want to look at really. So I'm going to close everything except pinned. So these tests all have very, very complex looking array accessing code in them. So we're checking offsets, and basically I have to make sure that my numbers are right here and do the mental mapping between this list of cells into these coordinates, and frankly it's just really, really unobvious. So by expressing my test scenario in this way, can at least check visually that my test cases are correct. So given DDD, I expect to get the same thing in return, and I can make that test pass by doing nothing. And that is interesting. Something has changed. So the reason this has changed is gameboard to string hasn't been overloaded. So what I'm going to do here is actually implement that. So we're just simply going to concatenate and return this. So sp equals new string builder. No, not string assert. String builder. SB append line. Return SB to string. So now I expect that test to go green. And it doesn't. Why doesn't it? I reckon it's because we've got a trailing new line. There we go, exactly that. Great, no problem. Trim. Okay, so this is a little bit ugly, but it's totally fine. It renders the game board correctly. Excuse me. Okay, so we've got these tests here. That proves nothing happens. So the scenario in which a cell becomes alive is if a cell has 3 living neighbours. So if we take this test, cells are dead cell has 3 living neighbours. Around it. It lives. Nice and simple. So at this point I would start refactoring away from this because I think this is going to get very, very visually repetitive. I'm going to leave it there for now though because I think it serves the purpose of a visual check. So given 3 living cells around it, so let's say this cell here is dead, this one here is alive. Actually, I'm changing the wrong cells here. I want to change the cells up here so that this is alive, and this is alive. So this D in the middle here, I would expect to come alive, and it should come alive because it's surrounded by 3 living neighbours. So my anticipated output of the first step is that. Great. So let's implement that rule. So to make this a little bit quicker, I'm just going to borrow a little bit of code from the original Game of Life board. Not any of the actual implementation there. I'm just going to borrow this. Actually, I'm not going to borrow this loop. I need that bit. So let's kill the middle. So what I've got here is 2 loops. So we're first going to iterate through the y coordinates. So the height of the Game of Life board, and then we're going to move across each line horizontally. So this cell is state x and state line offset, so y x, I believe, and I'm going to say if this cell equals triple equals, no JavaScript, equals D. I want to build up a new state really. So new state, new list string. Actually, the first thing I'll do is I'll get this cell and I'll add it to the new state. New state. I'm going to have to maintain a line, so this line equals that. New state plus equals this cell. state this line, and then new state, add this line. And then at the very, very end, I'm going to assign state to new state. So the reason we do this is we've got to operate on the whole of the game of life as a snapshot. And we're going to have to take off read only there. So I think here, what we're going to see is the first test still passes, because even though I'm modifying the state, making sure that it does nothing still works, but this one still fails. So now I have to establish the new state. So let's say var new state equals, so I'm going to pass it the existing state. Actually no, the existing states are private, so I'm just going to pass it new state for work out state x, y. And resharper very unhelpfully is going to do that. So let's pick up that and put it in there, so I can get this cell. And we're going to put the new state there. So the first thing we're going to do is we're just going to return this cell. Nice and simple. Nothing to see here, and we'll find the first tests still pass, and then this one still fails. And we're going to call that transformed, and we're going to do that. And actually, we're going to inline it. So this line is calculate new state. Great. Okay, so we're at a place where we've not implemented any rules. Let's implement the first rule. So if the cell has 3 living neighbours, the cell lives. So again, I'm going to cheat and steal a bit of rubbishy implementation. So this is fairly ugly code, but I'm going to borrow it. So let's do that. Neighbouring cell. I'll work out why that's not working. So getting neighbours x, y. Actually, it's more like that. And the neighbours are a list of strings in this case. List of char, of course. Great, so that's code that I've just lifted from the previous implementation. So to calculate a new state, I get the current cell. I'm going to pick up its neighbours. And then if 3 of them are alive, the cell lives. So firstly, if this cell equals dead, so if the cell is dead, if neighbours count alive is, so if the count of alive neighbours is greater than 3, exactly 3. I think this is a char again. So if the cell is dead and the neighbours are 3 alive, return A, make it alive. So interestingly, it's not falling into this. So I'm just going to debug through this and see what I get. So for cell 0, 0, the cell is dead. It has 8 neighbours and they are all dead. And what I can do here, if we check my test scenario, so 0, 0, I expect this to be now 0, 1. So x1, y0, yeah. So I'm going for the first line in my state, getting the second element, so that's alive. The neighbours are all alive. Which kind of makes sense. No, I'm not sure it does. This cell is 0, 1. Take a look at the neighbours, so the coordinates of the neighbours 0, -1. Ah, there's a bug. See, copying and pasting is the devil. Pair Y, pair X. And look, test passes. See, this is why you shouldn't copy and paste code. Really terrible idea. So in this case, if the cell is dead and there are 3 alive neighbours, we're going to continue. We're going to make it return A, transform it into alive. That's that one rule. And as we can see this transformation here. It goes from this state to this state, clearly. Okay, so the next test, which is if the cell is alive and has less than 2 living neighbours, it dies. Alive cell with less than 2 living neighbours, so it's 1 to 2 with 2 living, and if it's got 2 it lives, if it's got 0 or 1. Less living neighbours, it dies because it's lonely. So let's make all the cells dead again, and we're going to make this one alive. In fact, we can just make the first one alive. So 1 living cell, it's got, let's say, 1 living neighbour, it should die. 1 living neighbour, it dies, great. And that test fails, so we're going to come down here, we're going to say if this cell equals alive, great, so rules for alive. If neighbours, definitely not that, if neighbours count n equals, there's less than 2 living neighbours, okay. So alive is less than 2, return D, make it dead. So if this cell is alive, if the neighbours count alive less than 2, return D, and that test passes. This one now fails. Dead cell has 3 living neighbours around it, it lives, and that's because this has not been implemented. So let's fix this test. So this cell has 3 living neighbours, it should live. Let's check what our state is. Dad, DDD, expected dad, AAD. So on the second line, the first and third cell died. These two died here. And that kind of makes sense. So let's implement that rule. So if neighbours count n, and this is all getting very, very messy, but we're going to refactor it. So if the count of neighbours equals 2 or n equals 3, equals 2, or neighbours count n n equals, I like keep on typing triple equals, equals 3, return A. Let's just split this up. Oh, I see what I'm doing. I'm being silly. If n neighbours count of alive, if cell has 2 to 3 living neighbours, cell lives. Neighbours count equals 2, or neighbours count equals 3. There we go. Drop that in. Return A. It's interesting. It didn't quite get it. And if it has less than 2 living neighbours, it dies. Okay, well let's just implement that as well. So we've got less than 2, greater than 3. Less than 2 living neighbours, greater than 3 living neighbours, it dies. Less than 2, it dies. Greater than 3, it dies. If it has 2 or 3, it lives. So we've got a failing test here. The cell has 3 living cells around it, it lives. So I'm expecting D to return alive here. And what we've actually got is... so what's happened in the state transition is this cell up here has become alive. That's interesting. So let's check these rules. We're going to keep on going. So, has 3 living cells around it, so that doesn't. But what we'll do is we're going to make that one dead and see if this is the test that's broken. There are 3 living cells. That one's dead. I expect that to become alive. That one to die. I know that's alive as well because this also has 1, 2, 3. So when we go here, I would expect that cell to die. Interesting. Let's step through that and see what happens. That totally didn't work. Let's break into the first covering test at this line. So this is mcrunch being awesome. So I don't really care about the first one. The second one I care about quite a lot. So, first line, second character, calculate new state, so let's grab it. So it starts off alive. The neighbours, there's only 2 cells that are alive. This cell is alive, so it's not dead, it's alive. There are 2. So it stays alive, of course, because I thought it was 3. Just forgetting the rules of the game of life, it is accurate, it's correct. So because in this test these 2 cells are alive, this one stays alive, and likewise those will stay alive for that one, but this cell becomes alive, so that's a correct test now. So do we have anything we're not covering here? Neighbours count, so if there's more than 3 neighbours, it dies due to starvation, to overpopulation. Let's make sure we can have this. So, overpopulated because more than 3 neighbours. It dies. Great, so we can easily render this as well. So, let's start from our neutral grid again. So we want more than 3 living neighbours. So A, and A. Actually, let's do this in the middle because it's easier to see visually. So I want a live cell here with more than 3 neighbours. So 1, 2, 3, 4, crucially. And then 1, 2, 3, 4. The cell in the middle should die. I think that might just go green, but it's probably something else. A different cell would also die. So on the second line, expected AD, yeah, but we got AD, so the second line did correctly come out, but what I didn't calculate is the top line changing and the line underneath it changing, so that actually does look like my test is flawed there. So that's great, we'll correct the test. So that goes green because these cells here have 3 neighbours around them. So we're only really looking at this. I wonder if we can cut this test down so it's a little bit simpler. So more than 3 neighbours and it dies. So I wonder if I just pull this down here. Let's have a tiny grid. And the smaller we can make these test cases, the better. So if everything is dead, overpopulated because more than 3 neighbours. So I'm going to make this guy alive here. I'm going to give him 1 neighbour, 2 neighbours, and 3 neighbours. And I expect we're going to end up with 1 and 2. That stays alive. That stays alive, and I think this is going to come alive as well. No? I'm really bad at doing Conway's Game of Life in my head. TDD. So we're saying that is the correct state. Double A at the top. So why is this the case? So that has 2 neighbours. These are actually remarkably difficult test cases to render. So overpopulated. So this guy here has only 1, 2, 3 living neighbours, so he stays alive. This guy here has 1, 2 living neighbours, so he stays alive. Great. So, and the test I'm actually trying to write because more than 3 living neighbours. So I need to kill something with more than 3. So this guy here I can kill by doing that, I think. And he'll die. And I think also this guy will die. And maybe this guy will come alive. No, I really can't play this in my head. So that is that there, and this here. So it's interesting how difficult it is to isolate very distinct test cases in this. That's an interesting pattern. So 3 living neighbours, 1, 2, 3, so 2 or 3 means he stays alive. We can't really replicate more than 3 living neighbours, except here, so 1, 2, 3, 4, so he dies, great. But then this guy stays alive, yeah. So this guy dies because he has more than 3 living neighbours. Excellent. And we should hopefully see, yeah, test coverage here as well. So now we need a test case for if the neighbours are 2 or the neighbours are 3 and it's alive, it stays alive. That makes sense. Two neighbours, stays alive. Let's try that. Alive, 2 neighbours, stays alive. So again, let's reset all our game. So you're alive. You have 1 alive neighbour. You've got 2 alive neighbours. So this middle guy here should stay alive. I think this will just stay static. If I get the syntax right. And what didn't I do? Who is going to die? Ah yeah, so this guy now has too many alive neighbours to stay dead. And the guy at the top has too few, yeah. So you're going to die. And I think the one on the other side of him will probably also die, yeah. So the reason these guys are dying is because they're bordered on nothing, so nothing counts as no neighbours, so they're dying. So we'll take that. We'll do one final test with 3 alive neighbours to prove they stay alive. So here, if I take this guy and make him dead, and I say 1, 2, 3, oops. So in this case here, I expect this to be alive, because he will stay alive, and then both A's here have 2 neighbours, so I expect they will stay alive, and I imagine the one down at the bottom will also be alive. Yeah. Double A, double D, double A, double D. Yeah, that's exactly what I expected. Great. So now we've got test coverage of all of the various permutations of these rules. The first thing I want to do is make it look a little less ugly. So I'm going to take this here and I'm going to extract it. I'm going to call it replace 3 occurrences 4 by 4. Oh no, I can't do that. Game of life 4 by 4. And then you could probably make these read only. And great, so we've got a game of life 4 by 4. Actually, you know what? I don't like these being outside. I think visually it suits to see your assertions and the actual games here in a puzzle like this. So I like that. It's a lot more readable, so this is just iterating through. So the rules are still as ugly as ever, so let's refactor some of these things out. So this is property called dead. Surprised it didn't refactor all the others. So those are dead. Let's try that again. It's probably because ReSharp has special built-in support for refactoring strings, but probably not characters, so it doesn't make that much sense generally. So introduce field. Oh, worked that time. Alive. Let's just set this here. Dead equals D. So we've got our 2 states. And yeah, it's become a property down there that we don't need. This is just ugly, and maybe we'll rework that in a minute. But what we can see here is if we strip that away, if this cell is alive, if cell is alive and if cell is dead, great. And we can probably do something like this. Right, so if cell is dead, we're doing this neighbours count a lot. So let's refactor this. So we should be able to go control R, V, replace 5 occurrences, living neighbours. Great. So living neighbours. And then we can probably combine these 2 ifs. Should let us do it. There we go, so we can chop this out. So if the cell is dead and the living neighbours equals 3, we don't need this else. Actually, we don't need to check if the... we do need to check if the cell's alive. So if living neighbours equals 2, return dead. Less than 2, greater than 3. If it's 2 or 3, it's alive. We can invert this. So cell is not alive here. Let's just get out of there. And there are all the game of life rules. So what we actually have in this second attempt is much less code. So it's not quite as prettily factored. But what I'm going to do now is I'm going to quickly jump across to the program that I wrote the other night. And I'm just going to switch this to a game of life board 2, so I'm probably going to have to borrow one of the tests. I wonder if it's compatible with my state generator. I can't remember what the state generator was called. Cell generator. So we can generate a number of cells. Great. And that will return a random assortment of cells. Okay, cool. So let's just take a copy of this and we'll make another one. So for in our second game of life board, a different cell generator. I just want this to return a list of characters. The algorithm's identical. So instead of that is alive, enumerable repeat A, and enumerable repeat D, alive and dead. It's a list of char. And we're going to generate a new dead cell. And we're going to call 2. And I'm going to quickly hack in a public string generate map in number of cells x and int y. So what we're doing here is we're just going to say total equals x times y. That's the number of cells we want. But our cells equals generate cells total, and then we're going to say for upper x, actually we're just going to say dimension. So this is going to be a dimension by dimension. Well, it's less than that. Y is less than dimension, and all we're going to do is we're going to say string builder. And we're going to duplicate this up here. I'm not going to use I, so for Y, actually we're going to go across the X here. So X, X, X. Actually, it's exactly the same. We're going to loop around each Y, so for each, we're going to count up the lines. I'm going to say var string, not string, this line equals nothing, and then what are these cells? They're a generic list. Actually, screw it, let's just give it an initial state. I can't bother doing this again. I'm going to take this initial state and this game board. I'm going to open up the program. Let's just comment these lines at the top here. Initial state, and let's copy and paste that. Bam, 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 bam. 1, 2. And let's just make some random cells alive. So give it some state. So we've got some deads and alives. Excellent. Not sure what's going to happen. And then output is game board to string. Nothing more than that. And actually, we just say console clear, console write output. And then so we've got initial state and a game board. Let's run it. And yeah, Conway's Game of Life is playing, and we've ended up in one of the holding patterns. So the annoying thing here is it only works in A's and D's, and they're quite hard to look at, but they're quite good to test. So I wonder if in our game board constructor we can say char alive equals A, char dead equals D, and it will just allow us to overload these alive and dead characters. And yeah, that's private. That's private. And we'll take that and we're going to initialize alive. We take this and we're going to initialize dead. So we'll just use those default parameters. So what that means is if we go back to the program here, if I hit insert, actually if I take this, I'm just going to open up Notepad and I'm going to say file, replace. I want to replace the dead cells with a space. Great. And I want to replace the alive cells with a @ symbol. Copy that, paste it in there. Space obviously won't work because I'm using the trim. So let's use something different. Replace dead cells with a dot and alive cells with an @ . So if we do that, and then I pass it in, alive is @ and dead cells is dot. Might be a little bit clearer when we run it. There we go, Conway's Game of Life. And we've got another holding pattern, so I imagine it always, because the input is the same, it will play out in exactly the same way on the way out. Awesome. So that's pretty cool. And that took me about 35 minutes as opposed to 2 hours, and it just shows how writing the right tests drives out a much smaller implementation that actually focuses on the outputs that we're expecting, rather than all the, what I would probably describe as kind of architecture astronautism of inspecting internal state of object models and things like this. And really, the simplest implementation here for Conway's Game of Life is nothing more than a list of strings. That's pretty interesting. Just do a once over the code. I'm pretty happy with that. I'm actually pretty happy with these rules. So one of the things we could do is we could extract them into rules classes, but honestly with a game this small there's probably no point. It doesn't make any sense. So one of the things you could do is you could have a rule per thing. We could probably reduce this to some kind of dictionary. So I wonder if we could express this as, let's try this, state transitions, a little bit more declarative. State transitions equals new dictionary of initial string, and we kind of want an evaluation, so it's not even a string, it's a char, so whether it's alive or dead, and then maybe a bunch of funcs, something. So I want to open this up here, just call this object for now, and I want to say dead. I don't know whether this is going to be ugly or not, but it's worth having the experiment. So this is maybe a list of rules. So a list of expressions that, yeah, I mean, to be honest, we could probably have a list of expressions over a count of neighbours that returned a state, and it would make this code a little bit tighter, but I'm not convinced that it would actually be any more useful or readable, so we definitely wouldn't do that in this situation. So that's nice. Where do we use cell? Everywhere. If cell does not equal alive, I wonder if I invert this. That's horrible. If I invert that, again, not particularly nice. Then you notice that that removes this condition here, this line of untested code. And then, yeah, it's neither here nor there really. I definitely prefer the simpler direct read through of that. So, I mean, this is horrible. We don't really need a list of chords so much, but it's a nice little, I say nice, it's an ugly hacky way to quickly grab all of the neighbours. I'm sure there's a simpler way. And those were the old tests. So if you actually, now that we've done it, it's worth comparing. So we've obviously got some more bounds tests around invalid boards coming in, but so we've got tests that equate to that up there. We don't have any tests around what a dead or a living cell looks like, so we should probably have those here. So I would say test ctor given one dead cell, expect one dead cell. So the zero state transition rules, so game board was new game board 2. So it's interesting, this would normally be my first kind of test, but it wasn't because I so recently approached this problem. So game board 2, my state is nothing more than a dead cell. Assert that game board toString is equal to a dead cell. And we can likewise test those extra additions. So we can say given dead cell, in fact I would probably make a test case, so given dead cell, I expect a dead cell. Initial string expectation, T-A-T-I-O-N. So given initial expectation, great, nice and easy. I could drop an A, an alive, given one cell, renders correctly, so that tests the whole toString thing here. I could also say given one cell with, so actually I just want a single test for this, so given a live cell with overloaded render returns translation. So what I mean by that is if I give it an initial state of a single alive cell, but then I also say alive should render as that, characters. So if I say that, I would expect this to be my output. And it is not for some reason. And that's interesting. I wonder why that is. Let's find out. Where is the code? So I'm setting alive. Ha, that's interesting. It's probably because it's hitting this. If cell doesn't equal alive, return dead. And now it's gone green. So I can't actually do that. What I can do is I can invert this and remove that. No, I can't. I always have to return something. But actually, you can't get there. It's impossible. So if we come up here, it's going to be an exception. Interesting. So I've said here is one living cell, here it is alive. I want to step through this. It's because we're not performing any state transition at all. So it's never calculating the new state. Interesting. That's an interesting little bug, in that the overloads don't work when we haven't stepped, because stepping is the only time it calculates the state. Interesting. So the way we can fix this is we can say for each var line in for each line in state, we effectively want to calculate without doing a transition. So what I might do here is extract this, just give it a bad name for now, step internal, it's a bit rubbish, and then step should have an action on an X and a Y, and it returns a character. Great, so this takes a func on int and returns char. Great, I say action equals action, otherwise X, oh god, new func XY, and we don't actually have the initial state. Actually, let's not even bother trying that. I'll just say if action does not equal null, this line plus equals action XY, else this line. This isn't going to work either. Interesting. So calculating the new state, you know what, it's not really a realistic use case. It's my quick way of saying I don't want to do it. Actually, we totally can. So the default, if we say it takes an X and a Y, an initial, in int char, and returns a char. Wonderful method signature right there. That just can return initial by default. In char and then resharper will clean up all that syntax. So by default, if we don't provide anything, we just return the thing that's passed to it. So then this line plus equals action x, y, state x, y. Comment that out. Something still isn't building. Cannot change expressions. That should build. And we have something failing here. Oh, that's just the initial test, the extra test I've written here that's failing. So I think if I just call step internal, oh, that's just going to break everything. Great. Trying to be too clever for my own good. So let's just break into this. I'm going to step through it, see if it does anything like I expect it to. But it doesn't, because actually it'll happen on this line. if it's going to happen anywhere at all. Just get out the debugger. I'm going to step in here, step internal, so the action is just the default, I believe. So if I come into here, it's just going to return the initial state. Actually, we want our initial, that's why, we don't want that there. We want to pick this up here, and we want to say in here we do a transform. So if initial equals alive. This is actually impossible. The reason it's impossible is we're doing a translation without mapping between the characters, so this was a bit of a silly idea. So just for the sake of argument, I'm going to inline this. Oh god. There we go, this line. Let's kill that there. Bring that back. Inlining that method confused all of those variables, all the x's and y's. That's y, not y1. And that's x, not x1. And actually, that's never going to work unless we step. So I'm not going to bother with that for now. I could do it in a bigger test, actually. So if I did the same thing with AA, so 3 A's, everything is alive, that should stay alive, and I can say to string 0 is equal to ampersand, and it'll probably pass. Oh, because I didn't step. Game board, step. And now we get to make sure I did my state change in my head correctly, which I didn't. It's D. Let's try 1. Come on, one of them must be alive. What was it? 2 neighbours. So if I do that, one of these things must have stayed alive. Go on, what have we got? Let's just check this out here. DDD, overpopulated. AA, you guys stay alive forever, or you both just die? They both die. Okay, fine. Get a bigger one. AA. Let's just play around until I get an example where something stays alive. Go on, one of you must be alive. Ironically, it's probably easier to do dead. So if I do that, I can say that equals dead. I expected the string but was a character. Yeah, of course. So I know that if I pass it an A on its own, it's just going to die. For instance, I'd have to play around with the grid to get a translation test for alive, because I'd have to give it a valid circumstance that would actually stay alive. But broadly, you can see how the tests, in short, sorry, just lost myself, you can see how the tests represent the state changes of Game of Life quite happily, and if you run it, the game does play. Nice and easy. So compared to all these tests that are quite long-winded and quite finely grained, given that those are just a subset, because we've got tests around rendering here. So we've got the Game of Life renderer, and then we've got the renderer tests that test nothing more than drawing. Yeah, last time I was using hashes and dashes. There's also tests for creating, so game of life, cell generating, and cell generating tests. These tests would all stay. I just think the implementation of the game board itself is distinctly different if you drive out the tests from a visual representation. And that's it. That was my do-over. So thanks for watching, and I will see you next time.